Thanks to the organizers for having me. So I'll talk about an axiomatic approach to Nash equilibrium, or more generally solution concepts. And much of what I'm going to talk about is joint work with Felix Brand from Munich. Okay, so let me get right into it. The setup that I'll be talking about is very, very classical. So we consider finite normal form games. So every player has a finite set of actions and the game is given in normal form. And then a solution concept returns for every game a set of mixed strategy profiles. Good, so like one solution concept would be Nash equilibrium, of course. A non-example of a solution concept would be correlated equilibrium, because I'm asking here for a strategy profile consisting of one strategy for each player, not involving any correlation. In the second part of the talk, I'll talk about correlated strategies as well. Okay, but for now, let's stick with uncorrelated strategies. So in my examples, I will denote games like this. So here, all my examples will be two-player games, row player and a column player. And then the first number in each cell denotes the payoff of the row player. And then in this game, there is there is a Nash equilibrium that so one mixed Nash equilibrium that looks like this. So this strategy profile would be in the set of return profiles if we have the solution concept Nash equilibrium. Okay, but there would be other ones. Good, and then as to the axiomatic approach, so the name of the game will be to formulate axioms on solution concepts that are first supposed to capture rationality and some notion of coherent behavior across games. And I'll be more precise in a moment. And then we study which solution concepts satisfy these axioms, and ideally we can characterize particular solution concepts. Good, and this should not come as a surprise from the title, we'll characterize Nash equilibrium. So here are some more details on the axioms that we'll have in mind. The first one is totality, which says that the solution concept has to return at least one strategy profile for every game. Second one we call consequentialism, which essentially says that the labels of actions don't matter. So this axiom talks about clones of actions, where two actions are clones if they are payoff equivalent. So if you think of bimatrix games, then it would be two identical rows or columns in this matrix. So these are actions that are really only distinguishable by their label. And then the axiom says, if we take any game and we add a clone of an action to that game, then this does not alter the probabilities on the non-clones, and it also does not alter the strategies of the other players. And we can also do the reverse, so we can also remove clones, and then again, the strategies of the other players should not change and the probabilities on the non-clones should not change. And this is closely related to an invariance axiom that comes up in the literature.
So that also allows you, by once adding and removing it, to change the order. You make a clone of the second one and then you take that off and then
So yeah, so in principle you can also have more clones, you can go back and forth. Good. Third axiom we call consistency, which talks about convex combinations of games. So think about two games that have on the same sets of actions. So both games are of the same size. And the axiom says if the solution concept, if there's one strategy profile that's returned for both of those games, then it's also going to be returned in any convex combination of those two games. So one interpretation of this is that there is uncertainty about which of the two games will be played. And then if we look at the game before we know the outcome of the randomization over those two games, then the solution concept should also choose this same strategy profile. And instead of modeling uncertainty explicitly in our framework, we equate a convex combination of games with a randomization over games. And lastly, so far we have nothing that says something like higher payoffs are better than lower payoffs. So we'll need some notion of rationality. And here we have a very weak notion. It says that if a player has a strictly dominant strategy, then it should not be that this strategy is played with probability 0. Okay, so this is weaker than saying that an action that's strictly dominated receives probability 0. All right. And then the result is that the unique solution concept satisfying these 4 axioms is Nash equilibrium. Good. So I'll be more formal from now on. The framework is very standard, so we have a finite set of players labeled 1 to n. And then there is a universal set of actions that every player's action set in each game comes from. Okay, and we require this set to be infinite. So in our characterization, we will have to look at arbitrarily large finite games. And then a game is given by the utility functions. So it associates to every profile of actions a payoff profile, where an action profile is, well, it consists of one action for each player, and every player has a finite set of actions. Good, and then some more pretty standard notation. So delta AI will denote all mixed strategies. And whenever I say strategy in this talk, then I mean mixed strategy or possibly mixed strategy. And if I say action, I mean pure strategy. Then products of mixed strategies are strategy profiles. And again, so far only uncorrelated ones. And then there's a usual definition of the expected payoff of a player for some strategy profile. And throughout the talk, subscripts will correspond to players. A solution concept then is a function that assigns to every game G a set of strategy profiles. So in particular, we allow for multivaluedness. Good. And as I mentioned, Nash equilibrium is a prototypical example of a solution concept. Another one would be maybe pure Nash equilibrium, or various refinements of Nash equilibrium, or all rationalizable strategy profiles. And you could think of more examples.
When you say Nash equilibrium as a solution concept, you mean the entire set of Nash equilibrium?
Right, yeah. So the Nash correspondence.
The Nash correspondence.
Right. Yeah. Okay, so I think it's safe to assume that everyone here knows what a Nash equilibrium is, so I'll just skip over this slide. Okay, so then I'll give you more details about the axioms. Totality is pretty straightforward, so at least one strategy profile has to be returned for every game. Okay, so f of g is non-empty for every game g. For example, pure Nash equilibrium would not satisfy this axiom. Consequentialism, I will first define by example before I give a formal definition. So here we have two games, G and G prime. And let's look at G prime first. And then we obtain G by adding a clone of the top action of the row player. Okay, so we're just copying the first row. And then consequentialism will state a relation between the the strategy profiles that are returned for G prime and those that are returned for G. So it says that suppose this strategy profile here, for example, is returned for the game G prime, then if we introduce a clone of the top action, then any strategy profile where the column player plays the same strategy and the probability of the bottom action for the row player is the same, has to be returned in the game G. So in other words, if you introduce a clone, then the probabilities on the non-clone actions don't change, and probability can be distributed arbitrarily over the clones. And the axiom also goes the other way. If one of those strategy profiles on the left, well, lambda is something between 0 and 2/3, is returned in G, then the strategy profile here on the right is also returned in G prime. All right. So here's a definition of clones. It's two actions, BI and CI of a player I, so that for all action profiles of the other players and each player, the payoff of this player is the same no matter whether BI is played or CI is played by player I. Good. And then I'll define an operation on strategies that corresponds to shifting probability from one of the clones to the other clones. So here PI is some strategy for player I. And then this PI with a superscript here denotes the strategy where we take all the probability that's on CI and shift it to BI and nothing else changes. And then the axiom says a solution concept satisfies consequentialism if for any two games, G and G prime, so that G is obtained from G prime by adding a clone of an action, the set of strategy profiles that's returned in the game G are exactly the ones that we get by moving all the probability from one of the clones to the remaining one of the clones, if you remove the first clone. Okay. Any questions about this? Good. So then for consistency, I will also first give an example. So here we have two games on the same sets of actions, again denoted by G and G prime. And then the axiom will talk about convex combinations of these games, where by convex combination I mean entry by entry in the payoff matrices. And now the axiom says, suppose that the solution concept returns the same strategy profile in both of those games, then the same strategy profile should also be returned in the convex combination. Okay, and this has to hold not just for 1/2, but for any convex combination. Okay, good. So here's a formal definition. We have two games, G and G prime, on the same set of action profiles, and then we take any parameter for the convex combination, and any strategy profile that's returned in both of those games is also returned in the convex combination of those two. So note that we don't ask that the strategy profiles here on the left are uniquely returned in G or in G prime, and there could also be more strategy profiles returned in this combined game here. Okay, and lastly, so our rationality axiom. If we have So this is a standard definition of domination here. So BI dominates CI if no matter the actions of the other players, BI gives a higher payoff than CI for player I. And BI is a dominant action if it dominates every other action of that player. So this is strict dominance in pure strategies. Okay, and then solution concept F satisfies rationality if for every game and every strategy profile in this game, if player I has a strictly dominant strategy BI, then the probability of BI is strictly positive.
Isn't that enough to get non-emptiness? Because you can do your, can you get rid of non-emptiness, what you call totality? Because you can do the way, okay.
So in most games you won't have a strictly dominant action.
No, the way, but because you must have your convexity assumption, what did you call it?
Consistency.
When you average games,
Yes, so we do need totality. It won't be implied by the other axioms. Okay, so let me move on. The result is that the unique solution concept satisfying these axioms is Nash equilibrium. And it's an exact characterization. So, I mean, the first statement is Nash equilibrium satisfies all these axioms. Right? So Nash showed that Nash equilibria always exist. Then it's also pretty easy to convince yourself that this consequentialism axiom talking about clones will be satisfied because the definition of Nash equilibrium doesn't care about the labels of actions. The consistency axiom follows from the fact that fixing the strategies of another player, every player's best response constraints are linear constraints. And okay, rationality for Nash equilibrium should be clear as well. Good, and then there are two more statements in this. So first, every solution concept satisfying these four axioms is a subset of Nash equilibrium and also a superset of Nash equilibrium. Right, so this is how the argument goes.
Dominant strategy equilibrium is not acceptable.
Right.
Because it doesn't exist.
Right. Yeah. Also, pure Nash equilibrium is out for that reason.
If you drop totality, that's pure Nash equilibrium.
Yes.
Yes.
There's one more question.
Sorry. If there is a strictly dominant action, then that action in Nash equilibrium would be played with probability 1, right?
Right.
So why are we asking just positive probability instead of probability 1?
We could ask probability 1. You could also say for this, you could also strengthen rationality to say if an action is strictly dominated, it gets probability 0. Yeah. So basically, I'm trying to state the rationality condition here that's as weak as possible, but of course for Nash equilibrium more is true. Okay, I think you have next.
How is yours and your accents related to those that were in the literature in the 90s? They were, Thais and Pelling and Nord and so on. Yes.
Yeah, so I was.
Somewhat similar, but they're different, right? So
Yeah, I was planning to talk about those results more later. So, for example, the one you mentioned also has a consistency axiom which talks about different numbers of players. We fix the number of players and talk about games on different sets of actions. So it's a bit orthogonal in that sense. How we prove it? Yeah, I'll show it next. Yeah.
Just one last question. In terms of equilibrium selection, what breaks, for instance, if you look at just the any with, maximum social welfare or smaller and larger support?
So that was one of the next bullets. So you can look at your favorite refinement of Nash equilibrium, which axiom does it violate? For some of those, it's existence. and then, I mean, it really depends. For some it's consistency, for some it's consequentialism. Rationality will be satisfied by all of them, of course. Yeah. Okay, maybe one more.
Okay, or I can ask later, no problems. I'll ask later.
Okay.
So,
Okay, I'll continue. So two more remarks here. Yeah, please.
I wanted to ask about the consistency axiom, because that strikes me as the least obvious of the four. For example, one solution concept that comes to mind is players play their max and min strategies. That's going to satisfy the other axioms. It won't satisfy consistency, but that ruling out max and min because of consistency that maybe doesn't seem quite right. So I don't know whether you want to get into the justification of the axioms, but that seems to me a relevant issue.
Yeah, so I agree with the statement that the consistency axiom is the one that drives the most of the result and the one that's most controversial. There is this interpretation of randomizing over different games that I find somewhat convincing. But yeah, I mean, I think somewhere you need to get some leverage from. Good. So all of these axioms are needed for the characterization. And the proof that every solution concept satisfying these 5 axioms has to return a subset of Nash equilibria also works in subclasses of games that satisfy certain closure properties. So what you need is that this class of games is closed under adding or removing clones or taking convex combinations of those games. So for example, zero-sum games is an example of such a class. Okay. So I'm doing terribly on time, so, but I still want to give you some idea of the proof. Good, so the proof goes by contradiction. So assume you have a strategy profile that's not a Nash equilibrium, then there will be some player who does not play a best response. Okay, in our example here, this will be the row player. And then we'll try to use the axioms to get to a different game where this same player plays a strategy with probability 1 on actions that are not best responses. And I think this gives some idea of how the axioms work together to give the result. Good. So first step, we use consequentialism to get to a point where the row player plays a uniform distribution over a subset of actions, and you will see in a minute why this is useful. Okay, so here introduce a clone of the first action here, and then consequentialism tells you this strategy profile has to be returned, and I want to introduce an additional clone of this action. Okay. Good. And now another application of consequentialism, or one of the consequences of consequentialism is that you can permute the actions of a player and the strategy gets permuted accordingly. Good, so here these two games result from the first one by just permuting the rows, and since we have a uniform distribution here, all the strategies stay the same.
You define the mapping where AIs are sets, so you don't need any axiom for that. Since they are sets, the order doesn't matter. You don't need any axiom for this claim.
Yeah. Okay. So then we have 3 games where the same...
you need the order for convex combinations, I'm taking it back. You're cheating a little. Because to take convex combinations, you have to say what the order of the actions is in the set. Your definition of the game, you had a set A1. And now, when you take convex combinations, you have to say what the order you take in game 1, what the order you take in game 2.
So the labels do matter. We have 3 games here where the same strategy profile is returned. So that consistency tells us this should also be returned in the convex combination. So we get this game here. And now you can see by how we did this convex combination, the row player has 3 clones here. So let's use consequentialism again to collapse all of them and move probability to the remaining one. So now we have arrived at a situation where this player has all probability on an action that's a non-best response to the column player strategy.
In the probabilism irrational, this works?
No, this doesn't work. So you caught that I'm cheating here. If the probabilities are irrational, then you need an additional argument. So you do, like you approximate by a rational valued strategy, and then you take care of the remainder in the end. Yeah. Okay, step.
Do you assume that every game is a Nash equilibrium, or is this a result of some?
If I assume that every game has a Nash equilibrium?
Yeah, did you assume the family of games that you are dealing with?
No, I'm arguing by contradiction for this part of the proof. So I'm saying if the solution concept were to return a strategy profile that's not a Nash equilibrium, then in the end...
There are games that have no Nash equilibrium, and it's the Nash extension of the game that resolves this, right? I mean, there are games, if you don't assume mixed strategies fully, there are games without...
Yeah, I'm assuming mixed strategies.
You're assuming mixed strategies,
Yes.
so you're assuming Nash.
Kinetic is the product of delta AI. You assume that F goes into the product of the delta of AI.
Yeah, so it's finite matrix games.
Okay. So step 2 will be to move from a situation where one player has all probability on a non-best response to one where this action is dominated when restricting to the support of the opponent's strategy. So we won't get quite to domination, but when you restrict to the first 2 actions of the column player, then it will be dominated. And the argument here will be very simple to the one before, except that now we do the similar argument for the column player. So again, get to a situation where this player plays a uniform distribution, then use consequentialism to permute the actions of this player, and then we are again in a situation where we have games where players have played the same strategy profile, take a convex combination, and you get a game where we have clones for the column player, and then use consequentialism to collapse all of those. So now we have probability 1 on an action that's dominated if you forget about actions outside the support of the column player. And the last step will be to, again, use a similar argument to get to a game where the row player, where this action here is strictly dominated, or in other words, the first action is strictly dominant. So to do this, so we know that the first action is better, the first action of the row player is better against the first action of the column player. So what we do is make lots of copies of the first action of the column player. So in this case, 4 more copies. And then again, we will permute now the first 5 actions of the column player. So we only leave the last one fixed. And then again, average by taking convex combinations. Sorry, I was wrong. So we fix the first action and permute the last ones. Okay. So now I'm skipping the intermediate step and just showing the final game where all these actions are clones. And then you can again collapse them if you wish, or you can just observe that now in this game, the first action of the row player is a dominant action, but it gets probability 0. All right. So then I will try to very briefly say something about correlated solution concepts. So now instead of looking at strategy profiles, I'm looking at correlated strategies, so distributions over action profiles. And a correlated solution concept then is one that assigns to every game G a set of correlated strategies. And I'll say that such a solution concept is convex valued if the set of return strategy profiles is convex for every game. Good, and so a prime example of a correlated solution concept is correlated equilibrium. And so for the axioms we had before, most of them extend straightforwardly to correlated strategies. But for consequentialism, it's less clear. So there are two different extensions to correlated strategies. So let's have a look at that again. So first, good. So instead of looking at correlated equilibria, I'll consider coarse-correlated equilibria, because this is what I can say something about, where a coarse-correlated equilibrium is a distribution over action profiles so that no player can deviate to a fixed action BI before observing their signal. Okay. And then CCE denotes the set of all correlated equilibria for a game G. Good. And then here is the revised version of consequentialism for correlated strategies. So again, two games where one is obtained from the other by introducing a clone of the first action of the row player. Now, suppose this correlated strategy profile is returned for the game G prime, then consequentialism should say, if we introduce the clone, then probabilities of the non-clones don't change, and the strategy probabilities of the non-clones don't change. So this would say that on the left, all strategy profiles of this form have to be returned. So we conserve all the marginals for the column player. We don't change anything in the row for the row player that doesn't involve any of the clones. And then within the clones, you can distribute probability arbitrarily. And there would be, this is sort of a strong notion of consequentialism. There is a weaker one where we require lambda and mu to be equal. The difference between those two notions is that in this notion here, clones may provide different information about opponent strategies. Okay. And then the result is that any convex-valued correlated solution concept that satisfies these four axioms with the revised version of consequentialism has to be a refinement of coarse correlated equilibrium. Now, I should say that correlated equilibrium does not satisfy this strong notion of consequentialism that I defined, but it satisfies the weaker one, which I think may actually be the nicer one. So there is some open question whether that works.
How small can F be?
I don't know of another example than coarse correlated equilibrium that satisfies all these four axioms. So in principle, it could be true that it's not a subset, that it's actually equal, but I don't know. Good. And I'm afraid I will have to skip related work. So I'll just conclude here. So we have characterized Nash equilibrium with these four axioms. Also a stability version of this result holds. So every solution concept that approximately satisfies these four axioms gives approximate Nash equilibria in the sense of epsilon equilibrium. The result holds for some subclasses of games, or part of the result. And then for correlated solution concepts, coarse correlated equilibrium is the coarsest one, satisfying all of those axioms. I'll stop here.
I think that in decision theory and choice theory, usually the axioms are on the behavior of an individual decision maker. I think it's also the case in social choice. how is this related to this type of work? Because can you present the axiom as conditions on individual decision making?
So the short answer is no. So most of our axioms are inspired by this decision theory literature you mentioned. We can't formulate them on the individual level, and basically the reason is that the set of Nash equilibria is not exchangeable in general. Now, if you move to zero-sum games, for example, then you can do this. Then you can define a solution concept that works on the individual level, and basically the same axioms characterize maximin strategies.
The only axiom that works is convexity, right?
Yeah.
All the other axioms are individual. Non-emptiness, okay. Non-emptiness is something you get for free. That's
Also consequentialism requires some
you are-
coherence
you are
across
doing-
players.
For one player, you're doing a duplication, right?
Yes, but the axiom says
It
some.
says that it doesn't change for the
Yeah,
other
right.
players.
Yeah.
Sorry. What about the other part of the proof? You show one inclusion. Is the other one similar or completely different in spirit?
The other one is very much different, and as far as I can see, it doesn't provide much intuition. Basically, the rough argument is take any game, any Nash equilibrium for that game. You would like to show that the solution concept has to return this Nash equilibrium, and then decompose the game into, like, write it as a convex combination of games where this Nash equilibrium is the unique Nash equilibrium.
You have a dominant, strictly dominant square.
Right? And then consistency tells you it also has to be returned if you're in the convex combination of those games.
Thank you. Actually, I want to ask a bit about the consistency axiom. And philosophically, what I don't understand is the following. Nash equilibrium as a concept is a very non-linear, non-convex concept. So why does it make sense to ask for this type of invariance under convex combinations? I'm trying to get a sense of the motivation, because I could equally well imagine that, instead of taking convex combinations, taking some other combination of games might equally well characterize Nash equilibria. So, is there any reason for focusing on this? Sorry?
Best reply. He uses the best reply. Best reply is convex. Is linear in some sense.
Okay, but Nash equilibrium isn't.
I know, but he is doing it on the level of the best reply.
Yes, but we're not asking about unilateral convexity. We're not saying that every player will be using their individual coin. Yeah. Okay.
So basically what we, why Nash equilibrium satisfies this is because the output of a solution concept is a tuple of strategies. If you were to take the same axiom on the individual level, then it would not be satisfied by Nash equilibrium. But maybe you were more asking for a motivation of this axiom. Yes. And I think the best I can provide here is this interpretation of there's uncertainty over which game you will be played. And if you don't know the outcome of the randomization, you will still decide on the same strategy profile before knowing the outcome of the randomization. And you reduce randomization to convex combinations of games. But, yeah.
So my quick follow-up is this. Would this remain true, for instance? This coin toss example, you're saying that we do a coin toss. Would this remain true if every player was if the decision of the game was based on a different coin toss per player? On a different coin toss per player. If the coin was different,
no, I think
or biased differently.
No.
Yeah. Okay.
Okay, just one more quick thing. You had your hand up. You want to ask a question? Well, there was one. Use your microphone.
Thank you for your talk. The question is like you kind of characterize some axioms that in generic game kind of give you these conditions, and then you said something like in some subclass of games you kind of still get one of the inclusions. What are the axioms that you actually need for the equivalence to be, like for the both inclusions be true? Like is there a smaller family of games in which there is still the equivalence? What are the axioms of?
Yes. So basically, for the other direction of the result that I didn't show, you need that the class of games is sufficiently rich. Yeah. So it can't be too small. I can't give a particular class of games where the equality holds. I think in zero-sum games it may well hold, but it's yeah. I mean, I just haven't looked too closely at particular classes of games.
Maybe just quickly, so if you had, say, like a trembling hand equilibrium, what would be violated?
Okay. Trembling hand would violate consistency, right? Because basically the sequences that witness the fact that something's a trembling hand equilibrium could be different in two games, and then okay, yeah, you can see.
Index also violate convexity.
Yeah.
You can have +1 and -1, and then at the convex combination will be a 0, and many things can happen with index.